Hi everyone, this is VK. Welcome to Smid World. Here I am with another video.
MIPS maintenance bearings. Oil will for excessive clearance and light radial loading. This results in the oil film building up and forcing the journal to migrate around in the bearing less than 1 of RPM. Oil will is a serious condition and needs to be corrected. It can create metal to metal contact. A, sim- a symptom peculiar for journal bearing is oil will. It shows up as a vibration of approximately zero point 0.4 to 0.4x RPM. Oil will can be diagnosed by increasing the load, which will decrease subsynchronous vibration. Severe oil will cause looseness 1x or 2x. Journal looseness, rotating looseness. Peaks you can see CPM peaks 5x, 0.5x, 1 1.55x, 2.55x. Rotor rub. Spectra similar to mechanical looseness. It may be partial or full annular rub, often excites one or more resonance. It can excite high frequency. And the fifth point, cascade diagram and shaft orbit are very helpful in diagnosing the rolling element bearing. Why does bearing fail? Improper lubrication, contaminated lubrication, or heavier loading from unbalanced misalignment, bend shaft, etc. Improper handling or installation, old age. Bearing failure detection. You can see in the picture with the time. The graph you can see damage severity with the time. Bearing failure stages. Stage 1. Earliest indication of the bearing problems appear in the ultrasonic frequency ranging from 1200 K to 3600 K CPM. The spike energy, HFD, and shock pulse evaluate these frequencies. Stage 2. Slight bearing defects begin to ring bearing component natural frequencies, which predominantly occur in 30 K to 120 K CPM range. The sideband frequencies appear above and below natural frequencies at the end of stage 2. Stage 3. The bearing defective frequencies and harmonic appear. More defect frequencies appear and number of sidebands grow, both around these and bearing natural frequencies. When well formed sidebands accompany bearing defect frequency harmonics, bearing has to be replaced. Stage 4. Towards the end, amplitude of 1x and other running speed harmonics will increase. This creates bearing defect and component natural frequencies actually begin to disappear and are replaced by random, bold and high frequency noise flow. Third point, amplitude of both high frequencies noise flow and spike energy may decrease, but prior to failure, spike energy will usually grow to excessive amplitudes. The rolling element bearings. Fundamental drain frequency, ball spin frequency, ball pass frequency outer race, ball pass frequency inner race. RPM shaft rotation, rolling element diameter, D means pitch diameter, N means number of rolling elements, theta means contact angle. What do the bearing frequencies mean? FTF 0.381 RPM, BSF 1.981 RPM, BPFO 3.047 into RPM, BPFI 4.952 into RPM. During one shaft revolution, The cage rotates 0.381 revolution. The ball spins 1.981 revolution. 4.958 ball pass at inner race defect. 3.04 balls pass and outer race. Gearbox. Gear mesh frequency. Z1 RPM 1 equal to Z2 RPM 2, where Z is called number of teeth and RPM is shaft speed. Mating gears produce only one gear mesh frequency. Gearbox defects. Tooth wear out, gear eccentricity and backlash, gear misalignment, cracked or broken tooth or hunting tooth. Gearbox. Spur gear produce vibration in radial direction and helical gear produce in radial and axial direction. And side band spacing reveals the defective gear or pinion, and analysis should be done at maximum load. Normal spectrum, side bands, GMF and side bands, you can see all peaks are of low amplitudes, no natural frequency of gear at right head. Tooth wear, GMF may not change, high amplitudes of the side bands, presence of natural frequency of gear FN. You can see in the picture. Gear eccentricity and backlash, exact GMF, FN and their side bands, high amplitude of the side bands spacing reveals the effective gear or pinion. Gear misalignment, exacts harmonics of GMF with the side bands, amplitude 2 GMF or 3 GMF higher than 1 GMF. Cracked or broken tooth, high amplitude of 1 RPM of gear or pinion, excites gear and natural frequency. Time waveform indicates spikes at 1 RPM of broken or cracked tooth. Amplitudes of impact spikes in time waveform will be higher than 1 RPM in FFT. Hunting tooth, faults on both gear and pinion occur during manufacturing, causes high vibration at low frequencies less than 600 CPM. Gear set emits rolling sound. Gear set emits growling sound. Hunting tooth frequency, it is the rate at which a tooth in one gear mates with a particular tooth in other gear. For well-designed gearboxes, HTF is low. HTF means GMF, lowest common prime factor, by Z1 dot Z2. Z1 is equal to 63, Z2 is equal to 12, Z1 is equal to 63 equal to 7.3, Z2 equal to 12 equal to 3.2.2. Lowest common prime factor is equal to 3. HTF equal to GMF 3 by 63.12 equal to GMF by 252. Belt drives. Belt frequency is called RPF pi d by L. Belt frequency is the rotational frequency of the belt. Worn or mismatched belt will produce radial vibration at BF and its harmonics. Second part, the belt frequency often dominant with two sheaves in the system. Belt frequency is a subsynchronous vibration below 1x. Let's see the formula. Belt drive, eccentric sheaves. Eccentric sheaves will generate strong 1x radial components. A common condition, looks like unbalanced but shows at both sheaves. Drive belt, sheave misalignment, offset or angular type. Angular vibrations at 1x and belt frequency with the harmonics. Fans. Fan blade pass frequency equal to RPM x number of fan blades. Mainly radial vibrations. FB, FPF with 1x RPM sidebands, unbalanced horizontal or axial vibrations, inadequate blade clearances, uneven velocity distribution across fan inlet gives FB, PF vibrations. Pumps. Vibration signature depends upon operating condition, pumps, temperature, speed, cavitation, etc. Centrifugal pumps at vane pass frequency called RPM, number of impeller vanes and harmonics. Gear pumps at gear mesh frequency and 1x sidebands. And screw pumps at thread rate equal to RPM, number of threads and its harmonics. Electrical mode 10 measurements. Enveloping defects, low amplitude, high frequency, repetitive bearing or gear mesh defects. These defects emit repetitive low energy impact signals that are highly pulse shaped and of very short duration. They generate harmonics in the very high frequency range. These techniques filtered out low frequency vibration energies and therefore isolate and emphasize specific high frequency signals. You can see the IS42372 chart. Case 1 pump impeller wear summary. These case documents under HP monitor over a period of 2 years. An increase of overall vibration levels and the spectrum showed a high vane pass levels of 3 XRP. The pump has 3 vanes on the impeller and the internal inspection indicates impeller vanes. Impeller changed and both the overall level of vibration and the vane pass frequency returned to normal acceptable levels. Analysis. Overall vibration levels. Overall vibration levels were on the borderline of being in an alarm state for several months and remained stable. It was decided to monitor closely. Then suddenly overall vibration levels jumped to 0.95 inches per second, that is 390% change. The vibration spectrum. The frequency spectrum collected from the pump inboard bearing shows a predominant peak at the frequency of 3000 rpm. The spectral plot showing the historical growth in amplitude of this predominant peak. It is noted that the mission deterioration appears more severe on the basis of overall readings than on the basis of the frequency spectrums. One possible explanation for the observation is that there was an increase in vibration amplitudes and frequencies beyond the range. Theoretical consideration. The problems with blades and vanes are usually characterized by high vibration or near the harmonic frequency corresponding to the rotation speed x number of blades. Blade pass frequency usually exits in normal operating machines, but harmonics usually indicates problem. Problem diagnosis. The data collected pointed towards the pump impeller as a source of high vibration because of dominant peaks at the blade pass frequency as well as growing sideband hormone. Results. Corrective action. The pump impeller was removed and replaced. Findings. Overall vibration reading taken after repair amplitude significantly reduced. Conclusion. The objective of this case was to demonstrate the concept that the blade pass frequency, number of blades into shaft speed, and surrounding harmonics gives an indication of impeller conditions. These case overall vibration increase trend spotted the machine and change vibrating signature of the pump took on a new shape without high amplitudes and the blade pass frequency and the overall vibration level returned to